Okay, so I'm going to talk today essentially about a physical realization of the Riemann hypothesis. Because you see, to mathematically prove the Riemann hypothesis is a more complicated problem. So what I'm going to talk today is about a physical model that implements the Riemann hypothesis. And this is based on a paper that appeared in the Journal of Geometry and Physics. So I'm going to talk about the Riemann hypothesis and its relationship between complex scalings and the notion of logarithmic time reversal. So, okay, so the Riemann hypothesis essentially says that the only non-trivial complex zeros of the zeta function are located in what he called the critical line. So they are all complex numbers, but the real part equals to 1/2. These are the non-trivial zeros. They are trivial zeros that are located at the negative even integers. Okay, so this function has the trivial zeros that are located at negative even integers, but the non-trivial zeta zeros are given at those whose real part equals to 1/2. Okay, so 1/2 is what you call the critical vertical line on the complex plane. So this is a very complicated problem, and I think it's since almost 150 years, something like that. Okay, so the relevance of this hypothesis is that the distribution of the zeros, how they are distributed along this vertical line, there's a correlation also with the distribution of primes. Many people thought that the primes were distributed randomly, but apparently there's some, what you say, aperiodic order in the distribution of primes.
Yeah, they have discrete Bragg peaks and they're non-periodic, so it's quasi-crystalline order.
Yeah. So this is what Dyson suggested many years ago, that maybe there's a one-dimensional quasi-crystal that embodies the distribution of zeta zeros. But so far nobody has been able to come up with a quasi-crystal.
Because it's an infinite set of such crystals, it'd be hard to find.
So I guess maybe if you start from infinite dimensions and then you project down, you could maybe recapture them that way.
Have you looked at that paper toward the unification of physics and number theory? There's a geometric suggestion on analysis of the same pattern in the form of simplex integers and projections of n simplices.
I remember vaguely when I was here the last time you showed me something.
I think you'd find the paper interesting. There's a lot of good clarity in it in some parts. And it's an interesting point that you can analyze, if you analyze this problem through digital number theory, you may never solve it. It may be unsolvable, and it may only be solvable through geometric numbers, specifically simplex integers. So that's the argument that we put forth.
The simplex integers, I remember that when I was here, you explained to me a little bit about that.
They're ordered the same way. In other words, in an n simplex, let's say the n100 simplex, you have exactly the same order and distribution of prime simplexes as you would on the digital number line, but you have a lot more non-arbitrary structure than you do in the digital distribution. But it gives you the same information, the same 23 primes in the same order, etc. Yeah. It's in that geometry.
Yes. I would like to take a look at that again. Okay. Okay, so the definition of the Riemann zeta function is given by this power series, where the n are the integers, and s is, in general, is a complex number. And Euler showed that this summation can be rewritten, this infinite sum can be rewritten as an infinite product. So here you're summing over all the integers, and here this infinite product is over all prime numbers. And this series converges only when the real part of s is greater than 1. This function has a pole at s equals to 1. So what Riemann did is he performed an analytical continuation of this function to all of the complex plane, because the region of convergence only in this function only lied when the real part equals greater than 1. So what Riemann did is try to analytically continue this function for all complex numbers. And in order to do that, he used the Dirichlet eta function, which is defined like this. And it was through this function that Riemann was able to analytically continue the Riemann zeta function.
I have a question about this because but for this equality here, we use it to prove that the summation over the whole numbers from 1 to infinity equal to at the end minus 1 over 12.
So
is that assigning?
This is
assigning to this?
This is due to the analytical continuation. Because you are right. I remember Ramanujan also dwelled with that idea. How can you find an infinite number of add an infinite number of numbers and get a negative value? Yeah, it's what you call zeta function regularization in quantum field theory. But essentially, what you do is you perform an analytical continuation of the zeta function, and you go and you avoid the pole. So usually, when you avoid the pole, strange things happen. Yeah. But I think Ramanujan also is the one who gave a beautiful proof of that. Of course, when a series is infinite, if it's not absolutely convergent, the summation you can arrange the order of summation in any way you want, and you can get any number, any value you want. So there's a lot of strange things going on with when the series do not converge.
So, for example, you can look at the convergence of simplex integers by more than one value. You can ask, well, what is the dihedral angle series converge to? And that converges to 90 degrees at the infinite simplex, which is interesting because that's the same dihedral angle as the infinite cube. And then if you ask, well, what does the circumradii series converge to? And then that converges to 1 over square root of 2. So it's a different convergence than you get as phi squared over 12, or what is it, Rafe? The convergence of the digital integers. Yeah, pi 2 over 6, right? It's a different type of convergence. So in one case, you have a convergence with with algebraic irrational, 1 over square root 2, and in the other case, with digital integers, you have a convergence to a transcendental irrational, as related to pi. So it's interesting.
Yeah. That's right, because the zeta function, the zeta function for s equals 2 was pi squared over 6, right? Yeah.
And what is the value of eta of 1?
Eta is defined like this. So, of course, here it will blow up at s equals to 1. But here, you get a 0. 0 times infinity gives you something that it should be well defined somehow, or it's undetermined. Yeah.
It may be determined. It depends on who
it depends how fast one goes to infinity and how fast the other goes to 0. Yeah. But I think this function should be well defined at 1. I think. Yeah, because this is how you can analytically continue through 1. Anyway, so the idea is that Riemann was able to analytically continue his function to areas where the real part was less than 1. Okay, so now let's talk about physical approaches to the Riemann hypothesis. Hilbert and Polya, they had a conjecture many years ago that they suggested that maybe the non-trivial, go ahead. Yeah, the imaginary parts of the non-trivial zeta zeros could be connected with the eigenvalues of this operator. So they look at the spectrum of this operator. If you could construct an operator which is self-adjoint, then the eigenvalues of this operator will be given by the zeta zeros. And when I was here a few years ago, we played with the potential that was highly irregular, and we tried to construct a Hamiltonian whose spectrum reproduces the zeta zeros. Now in string theory, many years ago, I was playing with the scattering amplitudes in string theory, and I noticed that you find some sort of tachyonic resonance and tachyonic condensation in string theory. And I noticed that if there were zeros outside the critical line that violate the Riemann hypothesis, these zeros do not correspond to any poles of the string scattering amplitude. So I was trying to find a connection between the location of the zeta zeros and the poles in a string scattering amplitude. So I found that if there were zeros that violate the Riemann hypothesis, then you could find those zeros don't have a physical interpretation in terms of string scattering amplitude. So I know that Mike and David were very excited about this. When I saw them in Santa Barbara, they wanted to talk a little bit more about the idea of tachyonic condensates in string theory and these non-trivial zeta zeros. But what I'm going to talk today is actually even more, it's much simpler than this. The proposal I'm going to, here, I guess, anyway. Yeah, anyway. Okay, so I'm going to suggest a proposal which is much simpler than string theory and much simpler than the approaches we had before. So I'm just going to talk about a one-dimensional quantum mechanical problem. So this is as simple as you can get. So I'm going to construct an operator that is, okay, remember T is a positive number, you know, it's on the positive real axis. So what I'm doing now is quantum mechanics on the half line, on the positive line. Okay, so T here is a positive number. So I'm going to have an operator that is given by the derivative with respect to the logarithm. So this in reality is a scaling operator, because this operator really behaves as the generator of scalings. So I'm looking at scalings in one dimension. So think of the Fibonacci chain where I have dilations, inflations, and deflation. Okay. So what happens? I have an ordinary scaling operator, and then I'm going to add here, like what's the best way to characterize this term here? It's like a gauge connection. Imagine I add a gauge connection, like a gauge field in one dimension.
Yeah.
You know, as a simple, where now, of course, the gauge field is itself a derivative of a potential. So imagine I have a scaling operator and I have like a gauge potential in one dimension, and here I have an arbitrary constant, k. So I have a family of operators of this form, so I'm going to look for these eigenfunctions. You see, this operator, you know, is not self-adjoint. So because this operator is not self-adjoint, then its eigenvalues could be complex valued. So this is my eigenfunction associated with this operator, and S over here is my eigenvalue. In general, it's a complex number. So what I'm going to play is I'm going to have a bunch of wave functions parametrized by a complex number, and S will be related to the locations of the zeta zeros. So the idea is to try to relate the zeros of the zeta function with the eigenvalues of this operator. Okay, so the idea is that at every point in the complex plane, I'm going to attach an eigenfunction associated with this operator. Okay, so this is basically the idea. Now, okay, this operator is not self-adjoint, because when you work with the half line, you have to be extremely careful how you define the notion of self-adjointness. Okay, so there are many subtle things how you define the notion of self-adjoint. So, okay, so I have this operator. Now I'm going to look for symmetries. What are the symmetries that I'm going to be playing with? So I'm going to have the notion of a conjugation operation. You could think of like a charge conjugation operation, where I take to each eigenvalue or eigenfunction, I associate the complex conjugate. You see, I take S and I give the complex conjugate. So it's given by this expression. You know, I just take the complex conjugate of everything. Remember, this is real, but it's a complex number. So you can rewrite this expression in this form, like this. It's the same thing, you know. So this is like a scaling. So by complex conjugation, it's like a scaling. So because this is what I want to play, the idea with deflation and inflation. So I have my wave function, and I'm going to scale it in powers of t.
Are you making some kind of constraint in the function v? Because
no, the potential, you will see that I'm going to have an infinite family of choices. We're going to have an infinite family of choices.
Okay. This is imaginary, so you have a phase.
Yes. So what happens here is that this can be written in this form, you know, can be written in this form. This T is the same as this. It's like a face, you know. Okay, so it's like a U1 gauge transformation. Okay, okay. And then I'm going to define the mirror operator. Remember, previously I have this operator here, and I'm going to define the mirror operator because I'm going to have really with two Hamiltonians. So this is my mirror operator, which essentially is like replacing T for 1 over T. This is like an inversion. Also, when you have a conformal transformation, like a Mobius transformation, this is like an inversion. So I'm going to have another operator, which is like the mirror partner to the previous operator. So I have like a family of two operators, and I'm going to have a family of Hamiltonians. So I'm going to have everything is going to be pairwise, you know. And of course, this operator is not self-adjoint. So the eigenfunctions are given by the same, they have the same form, but now I'm replacing T for 1 over T. Okay? So the eigenvalues of this operator are given by S. So now I have my eigenfunctions are functions of 1 over T. Okay? So now I'm going to talk about how do I choose the choices for B. Okay? So I'm going to have an infinite family of choices, okay? And now let's suppose that you choose a family that is related to the theta series. You know, I'm going to choose an exponential of B that is related to, this is the Jacobi theta series, which is actually connected with the Bernoulli string spectral counting function. So it's like counting the states of a string, the modes of vibrations of a string.
It's also related to counting the number of points in the shells of E8 or of other lattices.
Something similar, yes, because I know for E8 you have a theta function associated with the theta with the E8 lattice.
With
yes.
each shell, yes.
Yes,
intersection of
you're
this
right,
grid
you're right.
and sphere.
Yes, the theta function is just it counts points. Yeah, yeah. Yes, so here you're counting the spectrum of this of the string. Okay, you can choose this. This is a choice you can make. Okay, there are many other choices. You know. Now here the L is another parameter. You see this L will be related. This L is an exponent. This L will be related to K. Okay, so K and L are interconnected. Okay. Okay, so now if you remember that the theta function of Gauss, you know, this is the way, you see Gauss defined his theta function like this, where he begins to count from 1 to infinity. Jacobi begins to count from negative infinity to infinity. It's the same function, but it depends, the starting point here, Jacobi sums over all modes, from negative infinity to infinity, and Gauss counts from 1 to infinity. So these functions are really related. I mean, they are just, for example, now when you invert this function, you get twice the Gauss-Jacobi zeta theory. So the most important thing is how does this theta series, how do they transform when you replace x for 1 over x? Okay, this is a key point. So this is so using the Poisson resummation formula, you can show that the Gauss-Jacobi theta series, when you make an inversion, is related to the old one times the square root of x. So this is a functional relation tells you how the theta series transform under inversions. Okay, this is a very key important relation, which also occurs in string theory when you look at T-duality in string theory. When you look at the partition function, or how a partition function transforms when you replace x for the inverse. So this is really connected with the notion of duality. The very large, how the very large is related to the very small. How the small scales are connected with the large scales.
Like the S duality.
S duality has to do with the strong weak coupling. Yeah, how the strong coupling is related to the weak coupling. T-duality is how the small radius is related to the larger radius. Yeah, yeah. So the question is that if you want to have this symmetry transformation, my parameters that I introduced at the beginning, L and K, cannot be arbitrary parameters, but they have to be constrained by this condition. So when and only when the parameters are constrained by this relationship, you can show that the wave function associated with the inverse is essentially given by 1 minus s of t. Remember, when you take the log of the inverse, it's like changing the sign. So this is like a time reversal from the logarithmic point of view. Under scaling, the logarithm changes sign. So this is what I call logarithmic time reversal. Okay? So the wave function and the logarithmic time reversal, this is how they behave. Okay? And then you'll see shortly why this 1 over t is connected to 1 minus s. Because if you look at the Riemann zeta zeros, maybe I can draw here. Or
on that one, Carlos, right there.
I'm sorry?
You can do on that one.
Ah, okay. So, yeah. Okay. So remember. Okay. So let's draw the. Okay. This is S0. This is okay. This is the critical strip of the Riemann. Okay. So remember here in the half line, you have this is where all the non-trivial zeta zeros are here. They are symmetrically distributed with respect to the x-axis. So if the Riemann hypothesis is false, it tells you that whenever you have a zero over here, the zeros are in quartets. There's always a quartet of zeros. Because given a zero here, when you take s and you go to 1 minus s, you are reflecting that zero with respect to the 1/2 point. Okay? So, and then when you take this one here and you reflect it with respect to the half point and the complex conjugate. So you will see that this 1 minus s is related to the reflection properties of the zeta zeros. The idea is that I want to implement the symmetries that the zeta zeros have with respect to the reflection points. I'm going to connect them with the transformation properties of these wave functions. And the t goes to 1 over t, and the charge conjugation. You see, on the charge conjugation, I take s and I take the complex conjugate, which is the same thing as taking a number s and taking the complex conjugate. It's a reflection with respect to the horizontal axis. And s goes to 1 minus s is a reflection with respect to the symmetry point. So this is the motivation to try to connect this quantum mechanical problem with the symmetry property of the zeta zeros. Okay. Now, if the Riemann hypothesis is true, then this rectangle is squashed, and everything falls into the vertical line. So it's like having the zeta zeros flow towards the axis. You know. Okay. So now I gave you a bunch of linear operators before, the mirror operators. They were like scaling operators. So because they don't commute, I can have 2 times 1 or 1 times 2. Because now I want to construct a Hamiltonian. You know, I gave you a linear operator, which is a scaling operator. Now what I want to construct is a quadratic operator, like a Hamiltonian, like a p-square, like a momentum square. So now I'm going to have my Hamiltonian, I'm going to have 2 Hamiltonians because I have 2 operators. And when these parameters obey this condition, I have something very interesting. I have that the eigenfunctions of my first Hamiltonian are given by s times y minus s. And my eigenvalues of my second Hamiltonian are the same. Okay? So now, look at how s and y minus s appear. You know, when you look at the non-trivial, at the trivial zeros, they live on the real axis and they're all negative and they're even. So what happens when you have those trivial zeros, what happens? S times y minus s is a real number, you know. But also what happens when you live on the critical line? When all my zeros lie on the 1/2 vertical line, this product is also real. Okay, so this product of s times 1 minus s is real only in the critical line or in the horizontal axis. Okay, so the location, so this is real at the location of my trivial zeros and the location of my non-trivial zeta zeros. So the idea is to look for some sort of a reality condition of my Hamiltonian operators. The problem is that because these operators were not self-adjoint, my Hamiltonian is not self-adjoint, so my eigenvalues are not necessarily real. You see? Because if they were real, then you will have a proof, but my eigenvalues, remember, these were complex numbers, but because these operators are not self-adjoint, my eigenvalues are not necessarily real. Okay, so I'm going to play with these relations. You know, I have a family of 2 scaling operators. I have 2 Hamiltonians. I have my eigenfunctions and my eigenvalues. Okay, so now what I'm going to do is I'm going to construct inner products of these eigenfunctions. So I'm going to define my inner product of 2 eigenfunctions. I'm going to define it as usual. You do in quantum mechanics. You take the complex conjugate, you take this one. Now my measure of integration is going to be here. This is like a logarithmic measure of integration, because I'm playing with scaling operators. So I don't have, if I throw away the t here, I will have like ordinary quantum mechanics, but here the scaling is fundamental. The scaling property of the zeta zeros, like this, how the primes scale, you know. So here, my measure of integration, this is the derivative of a logarithm. So the logarithmic scaling, so this is how I have this measure. And so then when I plug in my eigenfunctions, you know, and then I get my inner product, I get this, where now S12 is just this combination. Now what I'm going to do is I'm going to insert a trial function for B. I'm going to be playing with the remember, I told you that I could choose an exponential of v related to the theta series, and I'm going to see what do I get when I perform the integral. You know. Yeah. So what happens is that if you choose remember my exponential of 2b was related to the Jacobi theta series, right? So when I do the algebra, and then of course I'm going to notice that there's a singularity. You know, there's a zero mode, you know. So if you throw away the zero mode, you can perform the integral. And when you do the integral, what you're going to get is you're going to get an integral given by something called the completed zeta function. In other words, the inner product of those eigenfunctions associated with the Jacobi theta series, when you remove the zero mode, is going to give me on the right-hand side something which is related to the completed zeta function, and I'm going to tell you what it is, what the completed zeta function it is. You see, the completed zeta function is given in terms of the ordinary Riemann zeta function by this relationship. You know, I call it capital Z because it's not the zeta function; it's called the completed zeta function. You know, remember you have the zeta function here, and this is how it's defined. So the idea is that if there is a zero of the Riemann zeta function, you have a zero over here because they are proportional to each other. So the idea is that the inner product, you see, remember, this is an inner product. This inner product will be zero when there is a zero of the Riemann zeta function. So I'm going to have a correspondence between the location of the Riemann zeta zeros. There's going to be a one-to-one correspondence between the zeta zeros and the orthogonality condition between the eigenfunctions. So 2 states are orthogonal to each other if and only if they have a correspondence with the zeta zeros. Yeah. And you remember, if you this completed zeta function obeys the functional relation between there's this key functional relation, which you see over here. If you replace s for 1 minus s, you'll get the same integral, because this becomes this becomes this, and this is flipped. So essentially this expression over here obeys this symmetry relation. But in a certain way I cheated to you, because remember, in order to evaluate that integral, I had to remove the zero mode in order to have a well-defined integral, because otherwise the integral will diverge. But then I have a price to pay. If I remove the zero mode, there's a big price to pay, and the price to pay is that you will destroy this key functional relation. Because remember, if you remove the zero mode, remember here you're removing the zero mode, then you are truncating this expression over here, and you will lose the key symmetry properties which were essential to derive these functional relations. So you will lose all these beautiful relations by trying to remove the zero mode. So therefore you cannot use the theta series by Jacobi. You have to go and look in the literature and try to find another theta function that will help you, that will bypass this problem. So when I was in Santa Barbara, I met a mathematician. Let me see. I met a mathematician. His name is Coffey. So he has worked for many years on theta series. So he came up with a new theta series, which is called the weighted theta series. So if you throw away this and if you throw away this, you get the ordinary Jacobi theta series. So what he did is he introduced a weighting factor by a Hermite polynomial and these powers of n. So he introduced this extra factor in the series. So this is a new theta series, which is called a weighted theta series. And the advantage of this theta series is that you don't have to cheat. You don't have to remove the zero mode. You can now leave the zero mode in place and compute the inner products. So now, so essentially now you can go ahead and compute the inner products. And remember, now you can do this integral, and this integral converges when the real part is greater than 1 plus 2m. So now this inner product, you don't have to remove the zero modes. I'm sorry, let me see. Let me just go back here. Notice that you're summing from minus infinity to infinity. Now, notice that when n equals 0, then the zero mode does not contribute to the series. So you see the zero mode does not contribute because you have a 0 over here. So the zero mode is automatically 0. So you can perform the integral and you don't have to worry about the zero mode, because when n equals to 0, this is trivially 0. Okay? So you can do the integral, and this is what you get. So you're going to get this expression over here, and I will explain to you. This is a polynomial. This is a hypergeometric series, of this form. Don't worry about it. It's a complicated function, but it's a hypergeometric series. This is the Euler gamma function, and this is the Riemann zeta function. So in other words, the inner product, okay, let me see. So the inner product, I get something like this, okay? And this polynomial has zeros on the critical line. But the important thing is that now I can compute inner products using a new theta series. So now this is the key, that the zeros of zeta have a 1-to-1 correspondence with the zero inner products. Okay? So now again you have under the Poisson resummation formula, if you replace x for 1 over x, you have this functional relationship between your theta series, where j and m are arbitrary parameters, because you have a family of theta series and they are parameterized by j and m. They are just parameters who parameterize this infinite family of theta series. And now I'm going to look at the transformation. What's going to happen when I take this inversion operator, when I take t for 1 over t, these eigenfunctions, which are now given by this. Remember, my eigenfunctions are going to be, they're going to have the same form as before, but now this exponential is related to this new theta series. So when I replace t for 1 over t, what it does, it flips s to 1 minus s. Okay? That's the idea, is that when t goes to 1 over t, s becomes 1 minus s. So you have like this reflection over here. Okay. Yeah, I'm going to be as briefly as possible because, of course, some of this could be very technical, but I'm just going to give you the essence of that. Okay, so to sum up what I have done, I have a bunch of differential operators. I have a pair of differential operators, they are scaling operators. I can compute its eigenfunctions, its eigenvalues. Then I can compute their inner products, and then I can compute the Hamiltonians I had before. So now again, I have something very similar as before. I have my Hamiltonian given by d1 times d2, and hb is d2 times d1. These are my eigenfunctions, and my eigenvalues are the same as before. And remember, my eigenvalues are real only in the horizontal axis or in the critical Riemann line. Okay? And then, of course, this J and M, remember, S is the location, it's a complex number in the complex plane. It's a continuous number. J and M are arbitrary parameters that parameterize my family of infinite family of theta series. Okay? So I have an infinite family of theta series parameterized by J and M. And S is the location, is a complex number in the complex plane. And then, of course, if you want to see what happens when I perform a combination of a charge conjugation operation followed by a logarithmic time reversal. So what happens is when I take t to 1 over t, I replace s for y minus s. And when I perform the charge conjugation, I just take the complex conjugate. And then, the same thing with the other one. So the bottom line is that this state is an eigenvalue of my Hamiltonian, but now my eigenvalues are the complex conjugates, So you could play a little bit with the eigenvalues, with the eigenfunctions. So now I'm going to come to the key point, Now this symmetry operation could be linear or antilinear. I don't want to bother you, but remember in quantum mechanics, an operation is called linear. If you have an operator acting on a complex number, if the symmetry is linear, you can move the operator through the eigenvalues without doing anything to the complex number. Now the symmetry is antilinear if when you flip the sides, when you remove this operator to the right-hand side, then the eigenvalues acquire a complex conjugate. So this is called a linear antilinear action of an operator. And okay, so if there is, if I have a quantum mechanical problem that is CT symmetric, you have to have this. You have to have these relations. But let me just go back to the key point. Yeah, because this is because this is very technical. Yes. Okay, so then you can show that this eigenvalue is real only in the real line or in the critical line. But let me just go to the key point when the action is antilinear. Okay, this is probably the most interesting part. If the action of this operator is antilinear, by definition, when I move this operator past plus my eigenvalue, I have to take the complex conjugate. So this means when you take the commutator of my Hamiltonian with the CT operation, I get something which is trivially zero, because this is identically equal to this. So the difference is trivially zero. So this tells me that if this symmetry action is antilinear, my Hamiltonian is CT symmetric, because it commutes, the CT transformation commutes with my Hamiltonian. And then if and only if this action is invariant, it means that that when I transform my eigenfunction by a charge conjugation transformation and a logarithmic time inversion, what I get this state. But if this state happens to be equal to this one, for all values of s, then what happens? Then I'm forced to say that s equals to 1 minus s complex conjugate. And this only occurs when I live in a critical line. Okay, so let me reinforce the situation. I can, my symmetry, my quantum mechanics, if I look at the symmetries of my problem, if I have a physical system, I have this Hamiltonians, I have this quantum mechanical problem. If I have a symmetry under charge conjugation and this logarithmic time inversion, then if my states, if my vacuum, think of it as a vacuum, if my vacuum is CT invariant, it means that S has to be equal to 1 minus S complex conjugate, and this only occurs when S lives in the critical line. Okay, so the eigenvalues that parameterize my eigenfunctions obey this relationship, and this only occurs when S lives in the critical line. Okay, so in a certain way, I have an implementation of the Riemann hypothesis. I have a physical realization of the Riemann hypothesis because I'm giving you a quantum mechanical problem that realizes the Riemann hypothesis. But the key behind the Riemann hypothesis is realizing this symmetry over these scalings, these logarithmic scalings, these logarithmic operators, the inversion. So what I'm saying is that the Riemann hypothesis, they said, has to be connected with some sort of scaling symmetry and also complex conjugation. You know, okay. Remember, complex conjugation had to do with this U1 gauge symmetry. Remember the C. So they say U1 gauge symmetry, and the T is this T goes to 1 over T. Okay. So the Riemann hypothesis is telling us something about some sort of U1 gauge symmetry and this logarithmic time reversal. Okay. So I'm going to pause a little bit and let you digest, and then I'll continue. Hi, Clay. Does this make any sense, Clay? Because of course I would like to see this, how you could implement these ideas with a one-dimensional quasi-crystal.
Yeah, I wanted to see if after you're finished, I could get 10 minutes while the group is here to clarify something that I think makes contact with what you're doing here.
Yeah, let me just have some. Yes, go ahead.
No, and when you're done with this, Riemann presentation, if I could get 10 minutes to add something that ties it in to some, to some work that we've done here.
Ah, okay.
Can you think in direction like we're doing a deformation of the U1 symmetry?
I haven't thought about that. No. I have this is an ordinary U1 symmetry, but I haven't looked at quantum group deformations. No. You want to work on that? Yeah. But you see, Lapidus.
Wave function starts to have more quantum numbers.
Yeah. Well, the quantum numbers. Okay, remember, because S really, I was working with the whole complex plane at the beginning. Really, you have a complete, over complete set of states. Okay, that's another subtlety. But remember Lapidus, for many years when he worked on fractal strings and non-commutative geometry, Lapidus for many years, he believes that the reason the Riemann hypothesis is true has to do with this T duality. This T duality has to do with this T transformation. Yeah. And the reason you have a T duality in string theory is because you have a minimal length.
He's very geometrical minded.
Yeah, the minimal length and this T duality symmetry is crucial here. He believes that this is the reason why the zeros flow to the, you can think of this as the zeros flowing to the critical line. Right. I remember Terence Tao also has given some very nice talks where he thinks that the zeros that violate the Riemann hypothesis is like a gas. Then the zeros that live on the critical line, when they are not uniformly distributed, is like a liquid. And if the zeros were periodically distributed, it's like a solid. Oh, like a crystal, yeah. So in a certain way, due to this symmetry, you have like some sort of the zeros flow towards the critical line. Anyway, let me just go over here for a second. Yeah, let me just something. Okay, then it gets a little bit more technical, but let me see if I can find something useful. Okay. So when you so let me just summarize. When you take the location of the Riemann zeros, when you take this inner product for certain discrete values, remember this inner product after you do the integral, then you'll get a zero at the location of the zeta zeros. So this means is that you have a zero when this state is orthogonal to this state. Okay, so this is like, imagine this is like a ground state, and you look at the orthogonality condition of all the other states with respect to the ground state. This is, intuitively the idea. And then, okay, because I have a lot, I didn't want to bother you. This is all very subtle, blah, 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 blah. There was something that I wanted to tell you. Okay, simple conclusion. Using that weighted theta series, one can recapture the non-trivial zeros from an orthogonality conditions as inner product of these states with respect to a ground state. So you can think of this as the ground state. This is the orthogonality condition. You recapture the zeta zeros. And then, of course, the analytical continuation of the zeta function was essential. And then I'm going to just give you something about the theta zeros on inner products anyway. But let me just give you something which is to finalize, the relation to other work. You see, many years ago, Berry and Keating proposed a resolution of the Riemann hypothesis where they were working with a different Hamiltonian. They were working, this is Berry and Keating, with this operator, x and p plus px. When you remember, if x and p are quantum operators, they don't commute. So when you look at the Heisenberg commutation relation, you can rewrite this expression in this form. Notice that here you have a derivative of a logarithm. It's like a scaling operator like I had at the very beginning. But of course I have a more general function. What they have a 1/2 here. But remember, I had the gauge field. Remember, I had the U1 gauge field in my operator. My operators were more complicated. Remember, than this. So then what happens is that Bender, Brody, and Muller, they work with more complicated, they took this operator, and what they did is they perform a shift, like having discrete derivatives, like a forward, backward discrete derivatives. So they perform a shift, and they constructed a new operator, and they claim that the eigenvalues or the eigenfunctions of this new operator was given by the Hurwitz zeta function, which is a generalization of the Riemann zeta function, because now you have an n, but you also have an x, and when x equals to 0, you have the zeta function. So they try to prove the Riemann hypothesis working with a different Hamiltonian, But of course, it was just a proposal, another attempt to prove the Riemann hypothesis by working with the Berry-Keating operator, and deforming the operator by performing this shift transformation. These are like you take a function and you shift it by 1. It's like a discrete jump, like a random walk problem, So this is more connected to a random walk problem. And let me just give you some. Well, if you want to look at the references, because then we could talk a little bit, yeah. I'm sorry. I'm sorry. It sounds like hash.
That's a version 2.0. You just got upgraded to a third H.
Yeah.
It's better than a downgrade.
Yeah.
Thanks, Carlos.
I'm sorry. I know. I just sneeze. Yeah. Let me just see. Okay. Anyway. So this is. So I didn't. I mean, I could go on with the technical details, but there's no point really. So the idea is, okay. So here you have just a physical model, but remember, to mathematically prove the Riemann hypothesis is a more complicated problem, because you have to combine analytical methods with number theory methods.
You will need another relation between the zeta function and your wave
I know. I
function.
think you need to use number theory. This is what Terence Tao says, that you need to combine hardcore number theory and analytical methods like this one. Combine both of them.
So I think what Terence is missing is the simple principle of geometric numbers.
Can I sit here?
Yeah.
So we can talk a little bit. Yeah.
So, but I wanna, if I do the 10 minutes, does anybody have to go to the bathroom? So what I'm gonna say is all in the paper, defended toward the unification of physics and number theory. So I won't say anything that's outside the scope of what we demonstrated there. And whoever remembers that paper will probably be able to follow this shorthand, because I'm going to be quick. But it's interesting, okay? So, all right, so for any simplex, such as the 100 simplex, there is a quantity of n minus m simplices within it, which is exactly the quantity that are called prime simplexes. So simplex integer is just a number. It's a more powerful number than a digital number, because the essence of a number, as said by one mathematician, is the set theoretic combinatorics within the number. Now, of course, an arbitrary symbol, such as how we draw 5, does not have any self-referential symbolism in it, and it certainly doesn't in any way, as a symbol, describe the set theoretic combinatorics of the number, the integer 5. However, when you look at simplex integers as symbols representing integers, it not only gives you the numerical count of the integer itself, just as your arbitrary integer does in digital integers, but it also gives you the full set theoretic combinatorics in a very non-arbitrary way, in a principle called self-referential symbolism. So they're powerful, these simplex integers. And I want to describe a very important difference between digital integers, which are arbitrary man-made symbols as integers, versus non-arbitrary simplex integers. It can be understood with a simple idea. So when we're talking about the Riemann hypothesis and the distribution of primes, we're really trying to, it all ties in to the ability to predict the quantity of prime numbers that exist with some arbitrarily chosen bound along the number line. And so the method of, when we use digital integers, in order to get them to converge, we have to invert them. Okay? So when we do this and we continue the series to convergence, we see at the end this beautiful relationship to a number that you normally associate with geometry, which is pi. So we get this beautiful convergence written with pi. With simplex integers, we don't need to invert them. Okay, so I'm going to write pi here because I want you to pay attention to the fact that it's a transcendental irrational, right? Which means it doesn't have an algebraic expression. And when we use simplex integers and we study something such as the circumradii, the series, first of all, the circumradii series going from the 1 simplex to the infinite simplex ranges the span of 1/2 to square root of 1 over square root 2. So that's the span. So the circumradii of every single simplex integer fits within this bound. So if we only pay attention to the prime simplices, and it converges rapidly, okay? The distribution of primes thins out over as you go deeper down the number line. It becomes more sparse, and so we'll call that the numerical density. So the numerical density becomes more sparse with digital integers. The spatial density on the one-dimensional line also becomes more sparse over space. So spatially and numerically, you have sparseness as you go further down the number line. It's very interesting with simplex integers because the numerical density, of course, trivially, is identical to the, in other words, when you look at the density, when you look at the quantity of 23 prime simplexes within the 100 simplex, it's a trivial thing. There's 23, you know exactly how they're spaced out. So what you do is you take the circumradii of the first one of the first prime, which is 1, and that's 1/2, so you can draw that as a circle. And then you take the circumradius of the next prime simplex, and so on, and what you get is a set of concentric rings. And you can draw a line through the set of concentric rings to get a one-dimensional distribution. And numerically, that distribution drops in density identically to the distribution of prime density numerically. But unlike the digital integers, which also drop in spatial density, the distribution in prime density of the simplex circumradii on the one-dimensional line actually increases in density. It's very, very interesting because you go further and further down, and because of the extreme rapidity of convergence of this value to this value, which is a distance value, it far surpasses the increase or the rapidity of the thinning out of the digital. So you can get a ratio that you can study here for prime number theory. So you have this ratio which is with simplex integers, which is your spatial ratio, your spatial drop in density. So you pick a span and you say, I want to calculate what is the drop in density of prime simplex radii over space in 1D, and you get a number, okay? And then you'll get another number when you analyze what the density numerically is and how that drops. So this density increases, and this density, numerical density, decreases. And for some span of primes, there's a calculable ratio that can be used. So you can go to different equal spans along the number line, and you can check, is the ratio of these two, this increase in density and decrease in density, is it the same no matter where I go? Does it change depending on what span I take? And what's the rate of that change? How can I analyze how it changes from span to span in terms of the ratios of these numbers? The point that I'm making is that there's more rich and non-arbitrary information in simplex integer number theory than there is in digital number theory. So the next thing that I'll add to this is two problems. The first is that problem that I just defined. You know, it's been some years, but I don't want to be too distracted from prime number theory. But I want to tell you about quasi crystals and how it relates, and this is the second problem. It's a harder problem. That problem that I said is a one-day problem for someone like, you know, Ray or Todd or somebody who's played with this. And it's a problem that's never been written down in the literature, I'm sure of that, from the research we did when I made that paper. The other thing is quasi crystals. So Freeman Dyson says, he argues and explains from a mathematician's point of view why the distribution of primes and the distribution of non-trivial zeros is a quasi-crystal. So the thing about quasi-crystals is one can say that a proper quasi-crystal is some unknown irrational projection of some unknown periodic lattice in some unknown dimension. Okay? So the problem is that set is so large, it's an infinite set. How do we know, how would we possibly know how to start searching through that set of projection, hyperlattices and projections that would generate the same aperiodic point set that you get on the distribution for the non-trivial zeros or the prime numbers themselves. But what you can do is you can understand that each prime simplex maps to an A lattice, right? So an A series lattice. So for example, the simplex integer for the number 4 is the 3 simplex because it's the equidistant array of 4 points in 3 space that describes through its lower dimensional simplices the exact set theoretic combinatorics for the number 4 or the number 1,000,000 or any number. And so then you can extend that and you can say, well, can I study prime number theory through these geometric numbers by the A-n lattice series? And of course you can, such that within the A100 lattice, you have within it 23 prime A lattices. And the distribution of those prime A lattices within the A100 lattice is exactly the distribution of primes on the number line. And so where you want to try to do analysis is by irrational projection. So you can project that A100 lattice down to 1D by an irrational value. And you will get a point set, which is quasi-crystalline in 1 dimensions. Now the trick is, how do you isolate out in that projection the prime A lattices so that you can study the distribution of prime A lattices within this point set? It's a very tricky and confusing problem to think about. But I stopped thinking about it because I felt it was distracting our physics work.
Can I repeat the problem?
So I described one method of doing prime number theory by studying the ratio of the drop in density numerically over the circumradii of the simplex series, and as a ratio of the spatial density, which increases. So it's the prime number, the prime simplex. So let's say this is a prime radius, and this is not a prime radius, and this is not a prime radius, and so on. And you have a distribution where you say, I'm only studying in this series of circumradii of these simplexes the distance between the radii, because they're numbers that are lengths. So then you have this aperiodic distribution of points that represents the circumradii of the prime simplices. That's one way. And that's the one problem that I suggest is about a day's work of somebody who understands this, and it's not a hard problem to work, program a solution for in Mathematica and kind of understand. But a really hard problem is a more sophisticated way using quasi-crystal mathematics, and that would be to understand a simplex by extension into the A lattice. So the simplest n-dimensional building block of any A series lattice, A2, A3, and so on, is the n simplex corresponding to the A series lattice. And so similar to the statement that the distribution of 23 prime simplexes within the 100 simplex is exactly the distribution numerically of the digital integer primes within the span of 100. I want to come back to this for a second, because the way that we study the Riemann hypothesis for 100 years in prime number theory is to use the prime number theorem, and it's a way to predict in every case, an incorrect prediction of the quantity of prime numbers within a bound. It's never right in any case, but the larger your span of numbers that you're counting primes in, the more accurate the prime counting or prime number theorem counting method is, so that if you go all the way to infinity, okay, it would be accurate, but any finite bound is always inaccurate. And it's the inaccurate. So for example, when you're doing 100, the prime number theorem, which is based on the other most popular transcendental number with no algebraic expression, E, that gives you a significantly wrong number. So they're 23, it gives you 19, very wrong, right? And it's the wrongness, through a really complex mathematical process, it's the wrongness of the prime number theorem prediction that maps to the non-trivial zeta zero distribution. That alone is a very sophisticated proof that I don't even understand, but that Ray assures me is true and that we put in the paper. And it's in our paper. But I couldn't reproduce the math to show that mapping. But let's assume it's true. So then, therefore, the deepness of proving the Riemann hypothesis is understanding why this prime counting function based on a transcendental number is always wrong in every case, and how that wrongness maps back to the distribution of the non-trivial zeros. The non-trivial zero distribution is very much the same problem in a more sophisticated form as the problem of understanding what in the world causes and allows one to predict the distribution of prime numbers in any bound along the number line. So as you can see, when you analyze this question, why would there be 23 prime simplexes within the 100 simplex? Okay, you can clearly see the answer to that question, the way I've posed it, is a purely geometric question, where geometry makes contact with set theory, group theory, number theory. But it's a deeply geometric problem nonetheless.
So I remember you play with these binomial coefficients, remember?
Yes,
With those simplices, and I remember that it was a relationship between the binomial numbers, remember, Ray?
Yes,
I remember, okay, I remember vaguely, yes.
So I don't want to go over my time, but too much more. But Marcelo asked a question. I'm still in the process of answering it. And then Mia wants to ask a question. I'll let you go before me if you don't mind just going.
Okay, it's a very quick question. Not regarding to the Riemann concept, but in the beginning, what you say. Would you consider, so what's what do you think is so interesting about this prime and simplex? Would you say that it would be maybe words or letters in the code? How would you correlate this
to how we think about codes? Well, what we're doing is we're trying...
Infinite, right?
Yeah, I mean, how it might correlate, I'm not 100% sure, but there's a lot of papers, in addition to the one that Carlo and Ray and myself did on showing how there's this mysterious and very interesting correlation between quantum mechanics and prime number distribution and the Riemann hypothesis. It's very deep. Nobody has the convincing killer answer, because perhaps the convincing killer answer requires some deeper understanding of why it's been 150 years and we still are seemingly on the wrong track with proving the Riemann hypothesis. So back, is that okay? And so how it relates to the way I think everything is symbolism. And I don't like arbitrary symbols because anybody could make it up. I like self-referential symbols that are non-arbitrary, like mathematical objects such as n simplices. And those things encode non-arbitrary intrinsic meaning in mathematics. And so, of course, our whole program here at Quantum Gravity Research is about trying to use self-referential symbolism, of which form is quasi crystals, which are languages or codes made of self-referential symbols with syntactical freedom and so on. So somehow this eventually, when we figure out our program, we're somehow maybe going to have deeper insights into all of mathematics and number theory, and where does number theory converge with the physics, right? And
I think that definitely could they look like a very good candidate to being symbols and words.
yeah.
The only thing that I'm trying to understand, I don't know if we have I probably don't have the answer yet, is how this alphabet, this set of symbols would be infinite. Like why you would need this. I feel like it should be like limited in something.
I don't think you do need the infinite simplex series, but we know that mathematics is what nature is made out of. Most of us believe, like many other physicists, that nature is not approximated by our mathematics, that somehow we're starting to get glimpses of how nature is literally made of mathematics, and geometry is mathematics. So we live in a geometric reality. So it's this deep idea where you think about all of mathematics is an upside-down pyramid, starting with your choice of set theory or number theory, right? But in my opinion, counting numbers come first because you can't count sets without counting numbers. It's hard to study set theory without numbers, but we could say set theory is more fundamental. Okay, but just so you guys know, I have one more thing to say, which is answering Marcelo's question, and then I'm done, but we can put you first, Ray.
Yes, it will be short. I will just to explain to everyone here what is our geometric criteria of primality. It's that if you have a simplex of any dimension and you are counting the subsimplex of any dimension, for example, for a tetrahedron, you are counting the points, the edges, the faces, and you are coloring them, for example, for a tetrahedron in 4 colors, you should have the same number of point and element of each dimension of each color. And for the tetrahedron, it doesn't work, so this is proving that this is not a prime number. For the pentacoron, it works. Everything can be colored with 5 colors. So if you can see in high dimension and virtually make this coloring operation, you can, in one glimpse of view, see that this number is prime or not.
Okay. So on all of this,
Just
guys,
one comment on this.
Okay.
In the connection with quantum mechanics and quantum computation. So if you have a problem with more degrees of freedom, more qubits, you have a higher dimensional Hilbert space. But you always can decompose this and sound that we can translate this to like a higher dimensional simplice. You can decompose in building blocks, which is our lower dimensional simplest. Yeah, simple.
Okay, so I'll say the last 2 things, which I want to answer Marcelo's question, which was my problem number 2 anyway. And then I want to point out why I was emphasizing these 2 transcendental numbers. So prime number theory is deeply involving these 2 numbers. This is what the Zeta series converges to with another couple symbols here. And then the basis of prime number theory, whether you use one of the more modern derivatives of the prime counting function or the original one, it's based deeply on another transcendental E. And so whatever's going on, when you use this E, you get a mistake, an incorrect prediction, and then you map that prediction deeply to this Riemann hypothesis. So when you're dealing with simplex integer number theory, to do the same types of problems, but you convert into geometry, you use algebraic irrationals. And that's interesting. It may not be important, but it seems to be an interesting difference to at least keep note of in your mind. So now the last thing is just defining the second problem. So the second problem is to study the spectrum of prime distribution within a projection. So this was a kind of thing that's artificial. Well, this is a manipulation of if I were to take 100 simplex, I'd have to go around it and find all the n minus m simplices that are embedded within it, and then take their circumradii and then plot all their circumradii out where they share the centroid of these circles, and then draw my line through it so I can derive my one-dimensional spectrum of prime simplex distributions. So one question is, when I do that and I do a Fourier transform, do I get discrete Bragg peaks indicating a quasi-crystal mathematically, or do I not get discrete Bragg peaks? And so now, repeating what I said before, let's move beyond n simplices and take the extension of the n simplex series and study the problem the same way. So when we think of the simplex integer 3, it is the 2 simplex. And when we extend this out to its lattice form, we build out the A2 lattice. And so we can go to the 100 simplex again, which has 23 prime simplices within it, and we can extend that out to the A100 lattice, right? And embedded within the A100 lattice, there are 23 prime A lattices embedded within it. We take some irrational angle to project the A100 lattice to 1D. And the thing about irrational projections is they allow you to preserve a great deal of information about the higher dimensional object, whereas rational projections will cause you to lose a tremendous amount of information. So somehow, the conjecture that needs to be explored is how would one mathematically analyze this one-dimensional spectrum from some projection of the A100 lattice to pay attention to the density distribution over space and number and their ratio of the A prime lattices that are represented within that one-dimensional irrational projection. But you don't have to do it in one dimension. You could do it to any lower dimension, like 2D. But it's a hard problem. So Ray and I thought about it for a while, and then we had already, spent a long time on the paper and the research behind it and all of that, and decided to put the problem on hold. There is one more thing that I'll say relating simplices to prime numbers. So the prime numbers, when you study them via simplices, come in two mirror sets, which are equal. So if you go to infinity, half the primes are on one set in this base 6 structure and half are on the other. But we can understand the base 6 by first principles by taking we take the simplex series that gives the set theoretic combinatorics for each simplex, and that is Pascal's triangle. So when you look at Pascal's triangle, then what you're reading in that is the set theoretic combinatorics of any n simplex that relates to the line on that part of Pascal's triangle. It's the binomial coefficients. And then, so when you then study that, and this is explained in the paper, when you study that, then you realize, oh, okay, there's really a fundamental non-arbitrary bifurcation of the prime numbers when you study it via simplex series, the set theoretic combinatorics of simplex number theory, which is expressed in Pascal's triangle, and then you get these two lines. Now the lines are decreasing, they're increasing in wavelength. Okay, if you just were to draw them out on the digital number line, and then you understand that half the primes are on one of these wavelengths that increases in these waves that increases in wavelengths, and they're offset. But so then, again, what is most interesting to me is the extra information or ratios that you get, because in the case of what I suspect that maybe man-made integers in some weird abstract way are not natural or a bit artificial. In a way they are, in a way they are not. Okay, I'm not talking about the symbols, like how we draw 5. I'm talking about how you lose information, because here, when I use simplex integers, I actually have a different delta, a piece of information between this sequential pair of integers and the next sequential pair of integers. It's a different distance, but when you look at the distance between 1 and 2, and then the distance between 2 and 3, it's the same distance. So it's that homogenization, that loss of information with digital integers that may be the root of this 150-year-old problem, which is really a 2,000-year-old problem if you go back to the mystery of how to predict or understand the pattern of prime distribution. So I believe this is an easy problem, is a one-day type of simple problem, and this other thing I'm talking about is a very hard problem, because it requires, I could write this down and tell somebody exactly what to calculate. With this, I can't, because I can't tell you what the irrational angle should be. I can't tell you if it matters what irrational angle it is, and I can't even tell you how in the 1D spectrum how you would eliminate the non-primes so that you could study the spectrum. I don't know, but I believe there may be answers to it. But this way is for sure straightforward. This method here gives you real distance numbers in this, and then the ratio. So that's it. So it's a very juicy problem. It's not our physics yet, because we don't know what our physics is yet. But I have an intuition that there's a convergence in the future between number theory, prime number theory, and the Riemann hypothesis in particular, and fundamental physics. So if we were so bold as to speculate that our pathway is on a vector towards discovering nature's first principles, symbolic geometric code, then it's all very mathematical, and at the root of all mathematics is counting numbers, you know. So maybe but if I could find some person like Carlos or anybody that became interested, I'm going to give you the hard copy. Julia's giving you a hard copy now. If you study this paper, it's not like my essays. It's not talking about consciousness or a lot of essay type of stuff. There's some essay stuff in there because I can't resist, but what's in there that's rigorous, explaining this in greater detail, is very, very interesting. And you're so smart with both geometry and number theory.
Because remember, the connection between pi and the zeta function only occurs when s is even. When s is even, the zeta function gives you a number related to pi because of the Bernoulli numbers. So it's the Bernoulli numbers that hold an important key in that.
So I actually think that somehow, in a weird way, pi and e, these two transcendentals, are problematic. I'm joking, but I don't trust a number that doesn't have an algebraic expression. I'm joking, but I'm saying that between two irrationals, if one has an algebraic expression and the other doesn't, I trust that algebraic expression. You know, it's less controversial.
If I give you the simplex, the n1000 simplex, can you tell me immediately how many primes it has?
No, I can
Without
tell
counting.
immediately if it's prime or not.
We have an algorithm that'll tell you without any effort that it's prime.
Because of the binomial properties of the binomial coefficients?
It's by seeing,
The binomial
seeing all
coefficient.
the sub-components of the different dimension, given where their number is given by the binomial coefficient.
Okay.
So if you can see them in n dimension in one time, you can see the symmetry.
I have a question. What is algorithmically more economical? The method of telling Carlos that the prime 1000 simplex has n primes in it, or him giving you the digital number of 1000? In other words, if you had to do it by digital numeric means versus this geometric means, which algorithm to tell you if it's prime is more economical?
So with the digital number, I use the Eratosthenes Kribel, the simplest algorithm. So I must test all the number
One at a time?
before the square root of 1000.
So you got to do it by brute force?
By brute force with 33 number, and then I solve it.
And with the geometric, the simplex?
If I can see in n dimension, I can see it immediately.
Okay.
Well, but there's computational ways, mathematical ways to see. He doesn't mean visual. He means math. If he can mathematically, so it's harder.
Yes, I can see this for the triangle that 3 is prime, and I can see for the tetrahedron that 4 is not prime. But after that,
Okay, so not necessarily more, not more economical.
I see. But can you find a general formula, an analytical formula that predicts the number of prime simplices?
We didn't work a lot.
Do you have a universal formula that will tell you immediately if you plug in a number n equals 1000 and it will spit out the formula, or you can only do it by looking at the binomial coefficients?
yes, we have to look. I know that there is a universal formula which will give you only primes.
Yes.
But there is not a universal formula. You put a number and it will say it's prime or not.
So what
There is just algorithm.
So I say Terence Tao, at least in the United States, is the leading number theorist at UCLA. And all those guys are using more and more powerful supercomputers and insisting on digital integers. It's like they don't have another option, because they don't know, they haven't thought deeply to critically think about analysis by prime number theory, where you have more things to analyze, as I tried to demonstrate. You just have more non-arbitrary things to analyze and find ratios on. I'm not saying it solves it, for sure. I'm saying if we've spent hundreds of millions of dollars around the world in 150 years in modern times, and we're using digital number theory and now with supercomputers to kind of deal with statistics, how about not statistics? How about go back to the question of why is there 23, this is a geometric object. It's a thing. It's a prime 100 simplex living in 99 dimensions. Well, why is that? Why does it have 23 prime simplexes? Why is the distribution the way it is? So it's not just the count of 23, it's the distribution, the spacing. Like, why is that there? Then you can simplify that in the way that I showed you with the rings, looking at the radii, and you can study it. And I believe these two series, I mean, primes really thin out. So it should surprise you that the circumradii actually increases in density, because if you really understand how rapidly prime numbers thin, right? You should say, hey, I don't believe you, Klee. Why should I believe that they actually densify over the length domain? And the answer is, you'll find the kind of demonstration in the paper, but the answer is because although the prime density thins very rapidly, it doesn't compare to the density increase of the circumradii.
Because the zeta zeros become very dense. The spacing, as you go larger and larger, the density of zeros becomes very large. Actually,
inversely proportional to the distribution of primes on the digital number line.
Yes,
but they're just inverse. But
yes,
here, here the interesting thing is that they are different. That this, let me just explain what I mean here. When I go, Fong, what is the circumradius of the two simplex?
Square root of 3 over 3.
Like, just give me a rounded number. It is so this is 0.414.
Yes.
Okay.
So 1 over square root is 3.
So and this is 0.5. Okay. So this is wrong. 1 over square root. 1 over square root.
Should be larger. Should be larger.
I'm sorry. This is 7. This is 707. This
6.6.
Okay. This is 707. So what? So
0.06.
Okay. So 0.0. So look. So 0.06. So you mean
0.6.
0.6. So we got 0.6 from number 3 to number 4. We go to 0.6, which has already used up half, approximately, of your entire span that you have to stretch out. So when you start drawing these concentric rings, it goes like, and it densifies very rapidly, because the whole span is just 2.2. I mean, it's just the whole span is 0.2, right? Just the delta between this and this. So that convergence is much more rapid in density than the thinning of the prime distribution. So what I would study is I would start asking questions about these ratios. The first question I would ask is, well, if I take a really far, a far out span of 1 billion primes, right, but really far out, and I look at the ratio of these, and then I take another span further out that's the same size of span, and I look at that ratio. Are they the same? Or if I take a longer span that contains the same number of primes, right? Are those ratios the same? So there's several derivatives of the same type of question that you could ask. And by answering those, which are straightforward math things to solve, you start gathering some data points that then narrow your deduction or your next set of questions or guesses, right? And I think that should be studied. The quasi-crystal one's really hard, but it will produce, in principle, I can make the statement that in the projection of some A lattice to 1D, somehow embedded in that information is this prime A lattice distribution. But I don't know how to parse the information to study it.
And what do you think will be the irrational slope, as you call the irrational projection angle, that will get you from the A simplex to the quasi-crystal in one dimension? What is the value of that tangent? Is it rather the golden mean or not?
No, I try with many different ones, and it's always the same that we see, which is noisy. So I've not found a specific angle which is better than
Whose
the
slope,
other.
whose
The
tangent
problem
is a
for me
rational
is the
number.
projection itself. We should use something different.
We should clarify noisy. We have no evidence that it's noisy. When we look at the point distribution, we can say it looks noisy, but until we do a Fourier transform, which we didn't, and we don't know if it's noisy or looks noisy. And that's the thing about quasi-crystals with many inflations and deflations. Once you get past 2 and 3 and 4, 5 letters, you actually have a hard time visually distinguishing it between noise or chaos and non-chaos. You have to do a Fourier transform.
So you're only asking about the angle.
The angle when you project down to lower dimensions.
That's pretty much always related to the Fibonacci chain, which is arctangent and 1/golden ratio.
Okay.
But like, let's say you had the A4 lattice. You're saying you could just start with that irrational angle, so you take arc cosine
I'm
1/4.
not specifically talking about the A, but in order to have the Fibonacci chain, right? That's what we have. The Fibonacci chain corresponding to a periodic chain on the upper lattice, so that specific angle should be related to that.
That's a good idea. So maybe for any AN lattice, you can find that angle and get a complicated Fibonacci-related a golden ratio related quasi-crystal. So if we took A100, for example, then we would find that dihedral angle of the A99, the A100 simplex, and then try projecting that and see if that gets us to some interesting ratios between the two smallest lengths or something that has a golden ratio value. But Fang's right, even if it's not a golden ratio thing, it is a non-arbitrary angle. In other words, you don't want to just invent arbitrarily your irrational angle. At least taking the dihedral angle of that AN lattice is a good non-arbitrary choice.
I mean, so far the quasi-crystal we can kind of always find the Fibonacci chain in them, the one that we're interested in. Like A4, for example, if we generate the Penrose tiling, that's another case.
Yeah.
Right?
Yeah. But Carlos, so my request to you would be look at the paper, derive questions that you have that, I think it's all clear, but find questions. And who knows, you might get really intrigued with the question. And if so, maybe we could do a collaboration together. We could pay you a
What about your work on random matrices? Have you done any work on random matrices?
I would say a little, but not really a big
because
focus.
now you want to play. I mean, because now you're interested in tensor networks, right?
Yes. Now we are focusing on tensor networks.
Yes.
And my latest question is, so our irreducible quasi-crystals that construct our dynamic higher dimensional quasi-crystals in 3 and 4 dimensions are easily represented with matrix operations. However, when we look towards something like the Penrose tiling as a sort of interactive network of one-dimensional matrix operations, the 1D quasi-crystal subspaces, then we wouldn't have to go to a hypercubic analog of a matrix. So we call it a hypermatrix or hypercubic matrix. Wouldn't do that. You would perhaps you try to take a formalism and say, all right, each of these one-dimensional matrix operations, right, that are obviously based on like the Z2 lattice, those all network together in an H3 or H2 symmetric case of the Penrose tiling. And so how do we invent a tensor network formalism where eigenvalues of different matrix operations and all the individual matrix degrees of freedom for the one-dimensional Faison flips and actions.
What about when I talked to you guys about the string nets, when Avrik was here, remember? You had these ribbons in the Penrose tiling, and those ribbons look like string nets.
Yeah.
Remember, you guys did?
Yeah, but I want to restrict it and ask. Carlos, I want to ask. Look, can you take something like Elser-Sloan's quasi-crystal and derive from it a tensor network formalism where each one-dimensional path is described by matrix operations and eigenvalues, but that you network it not in a hypermatrix, but in an H4 symmetric tensor network?
I see. Okay, I have to think about it.
Okay, thank you everybody for giving me the time.